All right, so we talked about double slit interference. Now we're going to come back and add single slit diffraction. It's another wave phenomenon that we're going to care about. So what do we mean by diffraction? So for starters, diffraction is basically how a wave bends around obstacles in its path. So this could be a situation where, again, you have a hole, like what we talked about. So a doorway in a wall acts as a hole, or a window acts as a hole. And so we know that sound will bend through that so that you'll be able to hear what someone's saying on the other side of the doorway without having to stand directly in front of the door. Or you could have a situation where you just have a pole. So you're standing behind, say, a telephone pole, right? You're still going to hear the sound that's going around on the other, that's occurring on the other side of the pole, because those sound waves will bend around the pole to reach you. So basically this is a situation where your wave is going to bend. And so what evidence do we have of this? Well, again, as we just said, you can bend them around small obstacles, so you hear what's going on the other side of a small wall, or you hear what's happening if you're not standing directly in front of a doorway. And so if there was no diffraction, what would happen would be this, right? A wave would come through, and it would come straight through, and it wouldn't bend at all. And so in order to hear something, let's say this is a sound wave coming through a doorway, in order to be able to hear the sound, you'd have to basically stand right in front of the door. So you'd hear sound here, you'd hear nothing over here. And in fact, what we know occurs is you do hear sound when you're standing over here. So the fact that you don't have to be in front of the doorway to hear sound coming from, the other side of the door, as long as assuming the door is open, of course, that's telling you that diffraction does occur. All right. So again, given the way that we set up our interference problem, we said, well, part of what's going to happen is that there are going to be points where we actually see minima, because the wave coming from this source and the wave coming from this source are going to perfectly cancel out. And so we went through and talked about what situations you would get maxima, what situations you would get minima, so what angles of theta would you see maxima or minima depending on what you were making this path difference. Well, if we think about for a single slit diffraction, so instead of having two holes separated by a single slit D, I want to talk about having a single slit A. So you can think of this as basically looking at one of these and just blowing it up, right? So here's my single slit A, and then there's a principle called Huygens principle that basically says you can think of every point along this wavefront as the wave comes through this slit. Every point along this wavefront is basically generating its own wave. And so what we're going to care about is how, say, waves up here, or the waves generated by points up here, interact with points that are generated down here. And so it works out that what we're interested in is what's going on halfway down the slit. So when the wave generated using the Huygens principle up here, when it perfectly cancels out the wave that's generated right here, because the path difference happens to be some half wavelength plus an integer, then the same will be true for the next one down, the same will be true for the next pair, and basically you can pair these all up so that you actually get no light. So here's a situation where I can look at particular angles, right? I see this bending effect, I know diffraction occurs, but I'm also going to get points within my diffraction pattern where I get no, say, light. We'll assume this is a light wave coming through our slit here, where I get no light whatsoever, because basically points within the slit are going to interfere with each other to cancel out any light. And so you can see that, so what we're going to care about here is A is what we'll use for the slit width. So we're going to care about this triangle So it's got a hypotenuse of half the slit width, so this is A over 2. Again, here's the phase or the path difference that we're interested in. And so if we want to think about angles where thinking about this path difference at some angle theta, well, again, here's my right triangle. And so I know that the sine of this angle theta is going to be opposite over hypotenuse, so it's going to be my path difference over A over 2. And so all we're going to do is say, fine, let's just solve this for the path difference. And so the path difference is just going to be A over 2 times sine theta. And so if what we're interested in is points where we get cancellation, where we get a diffraction minimum, then I'm going to come back and take this path difference and say that those minima occur because I've got destructive interference, which means I need path differences equal to half a wavelength or 1.5 wavelengths or 2.5 wavelengths. And so when I plug that in on the other side, what I get is this is going to cancel out, and I'm going to be left with this situation where I get minima within my diffraction pattern for this equation. Here my m won't be 0, but it will be 1, 2, 3, and so this looks almost exactly like our equation for double slit interference maxima. The difference is that we've got the slit width rather than the slit separation. We don't have 0 included, and this is giving us a minima rather than a maxima. So this is where light is canceling out. So if you come and look and you take a single slit, this is the pattern you see. And so again, here's your central maxima, and then it's going to fall off to some point, some angle theta on both sides, where you're going to get your first diffraction minima. And then you'll have some light again, and you'll get a second diffraction minima. And part of what you notice is that the light actually fades out pretty quickly, right? So if I take 2 slits, part of what I notice is that my double slit pattern, it's very likely that my double slit pattern will show both the double slit interference, that's what these minima are, on top of the diffraction pattern, because both of my double slits will act like a single slit. So basically I'll have these points, say where I should have, so if I look right here, here's a maxima, here's a maxima, this should be a maxima. My interference pattern says I should be getting a maximum amount of light right here, but instead I'm not, because the light coming through each individual slit is interfering with itself to cancel out due to diffraction, so there's not anything to add up for interference. So I get a interference pattern lying on top of my diffraction pattern. And so there's kind of 3 ways that you can sort of see what's going on in dealing with slits. One is you can have a single slit with width, and you get your diffraction pattern. I can have 2 slits, and again, depending on how wide I make the slits, it'll be easier to see the diffraction pattern or not. So here, if I have a relatively wide slit, the diffraction pattern is easy to see. But you notice if I come back and make the diffraction pattern, or if I make the slit width very narrow, so keep the same separation but make the slit width narrow, what I've done is I've pushed my diffraction pattern out wider. So the minima for diffraction now happens way over here with my much narrower slits, and so it's not nearly as noticeable, and so what I see is mostly the interference pattern here. Whereas here, I see the interference pattern on top of the diffraction pattern. So I can sort of play with my parameters, the slit width and then the slit separation, to change what's going on with my pattern. Now again, you'll notice in the single slit pattern, again, I've got some bright central diffraction spot, maximum, right? Brightest here, and then it falls off. Here's my minima, there's my minima, and then it recovers a little bit, but it's not nearly as bright. The next minima Again, not nearly as bright. So what you see is this single slit diffraction pattern actually falls off fairly quickly in terms of its intensity. The double slit pattern, well, you notice that the double slit pattern, if you look here sort of across the middle, it keeps its intensity fairly well. And so part of what we're doing is we're basically taking this double slit interference pattern and we're putting it inside this single slit envelope. And so the intensity in our top pattern here, where we've got both single slit diffraction and double slit interference, they're both very noticeable, is because we're seeing this outer envelope that's dictating the intensity of the light combined with the double slit interference pattern. So you're seeing the minima, but you see these sort of very bright spots within the central diffraction maxima. In fact, these are almost bright enough that they start to sort of bleed together, and so the minima aren't very noticeable. Right? They're still there, they're just the brightness of these spots is sort of saturating what's going on in the picture, so it's hard to see, or it's at least harder to see, say, the minima here than it is to see that's what would be sort of the equivalent minima sitting out here in this much, much lighter, much, much dimmer second, or this much dimmer diffraction fringe. And so this is what you see in terms of the interference. This single slit envelope on top of your double slit interference pattern.